Hey everyone, in this video we are going to talk about certain digital components. Specifically, we're going to discuss decoders, encoders, multiplexers and demultiplexers. And then in the end we'll take a look at some exercises. So let's first start with decoders. Now, as you're already aware, information in digital computers is represented using binary codes. So if you have a code of n bits, it can represent up to 2 raised to power n distinct elements of information. Now this transformation from n to 2 to the power n is actually done within digital circuits using decoders. Decoders or binary decoders, it's the same thing. So a binary decoder is a combinational circuit that converts binary information from n coded inputs to a maximum of 2 to the power n unique outputs. For illustration purposes, here is a n to m decoder. So n refers to the number of inputs, m refers to the number of outputs. And since with n inputs you can have up to 2 raised to power n distinct values, that means m has to be less than equal to 2 raised to power n. So this is a block diagram for such a decoder. Here we have a 3 to 8 decoder. So it means this will have a 3 inputs and up to 8 distinct outputs, which you can see here. We have 3 inputs and 8 outputs, right? So this is how you basically represent a n-to-m decoder. So this is a 3 to 8 decoder like the one we saw in the previous slide. So here this is the logic diagram for the 3 to 8 decoder and the truth table for the same. So now you can see that this is the internal circuit consisting of the gates. We have 3 inputs, we have 8 outputs, and here we have the truth table for the same inputs and outputs. Now, there's an additional input that you can give to a decoder. It's known as enable. So enable is basically a on and off switch. So rest of the circuit remains the same, as you can see from the previous diagram. The only addition is there's an enable, and this line goes to all the gates within the decoder, all of these gates, right? You can see this blue line being connected to all the gates. So the point of having an enable is this basically works the same way this circuit does. It's the same thing. The only difference is this is now an on and off switch. So as long as E is 0, the decoder is not going to work. So you can give any input to it, there will be no output because your decoder is currently switched off. And when E is equal to 1, that means now the decoder is on and now it will work. So corresponding to the given inputs, it will produce the desired outputs corresponding to this truth table, but only as long as E is equal to 1. That's the only thing enable does. Alright, so as you know, NAND and NOR gates are universal gates. So basically you can design any circuit using NAND and NOR gates. So any circuit that you can design using any other gate, you can also design using NAND or NOR gates. So here we have a 2 to 4 line decoder designed with NAND gates. So all of this is again just for illustrative purposes. This is just a simple 2 to 4 line decoder. That means it will have 2 inputs and it will have 4 outputs designed using NAND gates. And here is the truth table. Now in this truth table you can notice something. As long as E is equal to 0 for all these values, given the 2 values for the inputs, you have the corresponding output values, right? When E is 0, you can give any 2 inputs and your decoder generates the corresponding outputs. When E is equal to 1, it doesn't matter what the inputs are, your decoder is basically not working. All the outputs are 1, right? So there is no correct output. It's just it behaves like an open circuit when enable is 1. Now I mentioned in the previous slide that your enable is basically like an on and off switch. So the circuit only works when enable is 1. Like in this diagram I mentioned it. So when E is equal to 1, your decoder will work. When E is equal to 0, the decoder will behave as if it's switched off. Now this is the same thing that's going on here. The only difference is we have an inverter here. That means when E is equal to 0, on this side it becomes E is equal to 1, right? That means when E is equal to 0, after passing through the inverter, it becomes 1. That means all these gates are getting E is equal to 1, right? So these are the outputs that the decoder generates. And when E is equal to 1, After passing through the inverter, it becomes 0. So now all the gates are getting 0, and that means the decoder is essentially, it's not producing any outputs. All right. So this is how your various kinds of decoders works. N to M decoders. Now, here's an interesting thing you can do with decoders. What if we need a certain sized decoder for a specific circuit, but we only have smaller decoders available, right? So what if we needed a 3 to 8 decoder, but we only have 2 to 4 decoders? So an interesting thing you can do with decoders is you can actually combine several small sized decoders to generate larger decoders. Here is an illustration. So here we have designed, using two to 4 decoders, we have designed a 3 to 8 decoder. And let's see how we've done this. So we have 2 to 4 decoders. So we only had these, but the circuit needed 3 to 8. So what we've done is, these individual 2 to 4 decoders, each of them will require 2 inputs and it will generate 4 outputs. So the 8 outputs part is fine. So we have input 1, it goes into the first decoder. It also, using this tap, goes into the second decoder. And then we have the second input, right? It goes into the first decoder. Using the tap, it goes into the second decoder. We need another. So these two inputs are now full, right? But decoders also have enable. Enable is also like an input, right? So what we can do is we can have a third input for our 3 to 8 decoder. We can have a third input, use it as an enable, right? So we can have an enable on top of the two inputs. So the problem is solved. These 2 to 4 decoders are getting these two inputs plus an enable, and on the outside this enable is actually our third input, right? And since we can't have the same enable line for both the decoders, we can use an inverter gate. So when this gets 0, this decoder gets 1, and when this decoder gets 1, this one gets 0. So this is how we design a larger decoder using a bunch of smaller decoders. Alright, now let's talk about encoders. So encoder, simply stated, is nothing but an inverse of a decoder, right? So in a decoder, we used to have n inputs and up to 2 raised to power n unique outputs. In encoders, we have up to, at most, 2 raised to power n inputs and n outputs. It's just the inverse of a decoder. Alright, so here for illustration purposes, we are showing an octal to binary encoder. Now, when we learned about number systems, I'm sure you must have learned how to convert octal numbers to binary numbers. That conversion you did by hand, right? And this is a circuit that actually does the same thing, but by using gates instead. So what we have is, we have 8 distinct inputs, and this circuit is going to give you 3 distinct outputs. So it's converting an octal number into the corresponding binary number. So this is just the Boolean functions and the truth table for this octal to binary encoder, right? So you either use these functions that will give you the corresponding binary number for the given octal number, or you can use this truth table. So these are the inputs and these are the corresponding outputs of the encoder. All right, now let's talk about multiplexers and demultiplexers. Now, a multiplexer is a combinational logic circuit designed to switch one of several input lines to a single common output line. So what happens is, you have a circuit with multiple inputs, right? And what a multiplexer does is, it picks one of those inputs and passes it as the output. So out of the several available inputs, one input is chosen and it is transmitted through the multiplexer as the output. So one of the inputs becomes the output. All other inputs are halted. And a demultiplexer does the exact opposite of this. So it switches one common input line to one of the several separate output lines. So let's discuss these in a bit more detail. Now here is a very simple block diagram of a 4 to 1 line multiplexer. 4 to 1 line multiplexer means it will have 4 distinct inputs, and a multiplexer always has a single output line, right? So 4 inputs, 1 output. We have A, B, C, D, 4 inputs and 1 output. And it also has select lines. So these select lines are actually what help the multiplexer decide which of these inputs will become the output. That's all a multiplexer does. It will pick one of these 4 inputs and transmit it as the output. And which input is selected is decided by these 2 select lines, by the combination of these 2 select lines. So here's the logic circuit and the truth table for a typical 4 to 1 line multiplexer. You can see we have AND gates, OR gates, and we have the select lines connected through inverters, right? And how this works is, when the 2 select lines are 0 and 0, both of them are 0, right? Output is whatever this input is, right? Q becomes A. When B is 0 and A is 1, these are the select lines. When B is 0 and A is 1, the second input becomes the output of the multiplexer. When B is 1 and A is 0, the third input, C, becomes the output of the multiplexer, right? And when both the select lines are 1, the fourth input becomes the output, right? So what these X's denote is, it doesn't matter what the value of B, C, and D are, because when A and B are 0, whatever the first input is will become the output, right? Similarly, if A is 0 and B is 1, then it doesn't matter what the value of D, B, and A are, because C is going to become the output. This is how a multiplexer works. So we have a 4 to 1 line multiplexer, which means we have 2 select lines, because with 2 select lines we can have 2 to the power 2, which is 4 inputs. So you see the relationship between the number of inputs and the number of select lines. All right. Now, how this input line selection works is illustrated using this very simple diagram, right? When A and B are 0, A becomes the output. When A, B are 1, 0, B becomes the output. When A, B are 0, 1, C becomes the output. And when A, B are 1, 1, D becomes the output. And naturally, if you add more control address lines, N will allow the multiplexer to control more inputs, as it can switch 2 to the power N inputs. Alright, so as the number of inputs increases, this will naturally have to increase. The number of select lines will have to increase, right? So for N select lines, you can have a multiplexer whose inputs are 2 to the power N. Now, a demultiplexer, like we discussed before, is the exact opposite of that. That means it will have one input. It will always have one input. It can have multiple outputs. In this case, we have chosen a 1 to 4 channel or 1 to 4 line demultiplexer. So this is the diagram, the block diagram, which is basically a flipped version of the multiplexer. We have one input, and we have multiple outputs, and we have the number of select lines, like we had in the case of the multiplexers. Here we have a very simple switch analogy and the truth table for a demultiplexer. So a switch analogy is nothing but, it's basically an illustration of how this thing works on the inside, how switching is being done, right? How this kind of switching is being done. This is what a switch analogy does. So in this case, we can see that these are the control lines which are going to decide which of these outputs is going to get this input. All right, which of these switches needs to be connected. Now you can see when A and B are both 0, the output is A. So this will get an output. This input will directly go here, right? When A, B are 0 and 1, B will get the output. When A and B are 1, 0, C will get the output. That means F will go directly to C. And when A and B are both 1, D gets the output. All right, and this is the logic circuit for this multiplexer. You can see again we have AND gates, we have the select lines connected through inverters, we have a single input, and the point is to decide which of these outputs is going to get this single input, and that is decided by the value of A and B according to this truth table. Alright, now let's take a look at some exercises, very simple exercises. Let's start with problem 1. Construct a 5 to 32 line decoder with 4 3 to 8 line decoders with enable and one 2 to 4 line decoder. Use a block diagram. So what you need to do is we are given 4 3 to 8 line decoders with enable and one 2 to 4 line decoder, and we are supposed to design a 5 to 32 line decoder. So this is basically what decoder expansion was all about, right? When we have to design a larger decoder using a bunch of smaller decoders. So let's see how we can proceed with this problem. So first, let's start with what we need to do. So we have a 5 to 32 line decoder, right? So let's first draw the 5 inputs, A0 to A4. These are the inputs for our 5 to 32 line decoder, right? Now let's put the first component that we are allowed to use, a 2 to 4 line decoder. This is a 2 to 4 line decoder. That means it will have 2 inputs, 4 outputs. So I've taken these 2 inputs and then this decoder will generate 4 corresponding outputs. So now I have 4 plus 3, 7 inputs at this point. Now we're also supposed to use 4 3 to 8 line decoders, right? So let's just put them all together. We have 1 2 3 4 3 to 8 line decoders, all of them, and these have enable lines as well. So we have 3 inputs for each of these decoders plus an enable line for all of them, right? So we're taking this step by step. These decoders will have 8 outputs each, right? So let's just draw these. So what this basically represents is, this is a simpler way of drawing 8 lines. Otherwise you could have drawn 1 2 3 4 5 6 7 8 individual lines, but instead of doing that we can do this as well. So it's a simpler way, right? Saves a lot of effort. So all of these decoders are now generating these outputs. All right, so we have how many outputs? 32 at this point. So we have 5 inputs, 32 outputs, which is what we were supposed to do. Now we just have to fill in the blanks. What comes here? How to connect these inputs plus these 4 inputs to all of these inputs to make the circuit work. So let's see what we can do. All right, first we can connect these 3 inputs directly because this is a 3 to 8 line decoder and I had 3 spare inputs here. Let's see, right? 1 2 3. So we can just directly connect them. All right, now let's see what we can do in the next step. Now one of the outputs of the previous 2 to 4 line decoder will become the input for the enable line, right? Because we needed an enable line for each of these 3 to 8 line decoders. So we have 4 spare outputs here and 4 enable lines, right? So each of these outputs will become the enable line for the 3 to 8 line decoders, right? And now what we're going to do is repeat the same process. A0, A1, A2 become the 3 inputs of each of the 3 to 8 line decoders, and the 4 outputs of this 2 to 4 line decoder will become the enable lines for each of these 4 decoders. This is the process we are going to repeat for the remaining 3 decoders. And this is what we've done here, right? And this is how the circuit is complete now, right? So we have a 5 to 32 line decoder using 4 3 to 8 line decoders with enable and 1 2 to 4 line decoder. So all you have to understand here is we just need to design a circuit which has the necessary number of inputs and outputs, and then we have to find a way to combine multiple inputs into a single input line if necessary, right? So if you have more input lines than what you currently need, you have to combine them. You have to use taps, or you can use a same line converted into 2 different lines using an inverter, like we did when we were discussing decoder expansion. So the idea is to either combine multiple input lines into a single line if you need to reduce the number of incoming input lines, or if the reverse case arises and you have to somehow find ways to increase the number of input lines. So you have to make 2 input lines using 1, then you can split the same input line, use an inverter in the middle, so that when one of the circuits gets 0, the other one gets 1, right? And vice versa. So that is all you have to consider in exercises that pertain to these kinds of problems, where you have to construct larger circuits using smaller circuits. Now let's move on to problem 2. In problem 2, we are required to draw the block diagram of a dual 4 to 1 line multiplexer and then explain its operation with the help of a function table. So what separates a dual 4 to 1 line multiplexer from a normal set of two separate 4 by 1 line multiplexers is that it will have a number of inputs corresponding to each of these two 4 to 1 line multiplexers, which means it will have a total of 8 input lines, but it will only have 2 select lines, right? If we had two separate 4 to 1 line multiplexers, they would have had a total of 8 inputs and 2 select lines each, which means a total of 4 select lines. But what happens in case of a dual 4 to 1 line multiplexer is that it will have 8 inputs, right? But it will only have 2 select lines. So this is what a dual 4 to 1 line multiplexer looks like. So you can see here we have 4 plus 4, 8 inputs, but only 2 select lines. And these 2 select lines actually control the operation of both these 4 by 1 multiplexers, right? So you can think of this as having two separate 4 by 1 multiplexers, but you have to be very careful because the number of select lines for a dual 4 to 1 line multiplexer will be 2 instead of 4. All right, so let's take a look at the function, how it works. So again, these two select lines are going to control the operation of this entire dual 4 to 1 multiplexer, which means just try to remember the function table of your normal multiplexer and apply those rules to this current setup, right? So what happens is when S1 and S0 are both 0, if you recall from the function table of a typical multiplexer, the first inputs become the outputs. So the outputs, which are YA and YB, are A0 and B0. Again, these two select lines are going to control both these sets of inputs. They will control A and B at the same time. So when both of these are 0, 0, A0 from this set of inputs and B0 from this set of inputs will become the output. Similarly, when these are 0 and 1, A1 from this set of inputs and B1 from this set of inputs will become the outputs, as we have mentioned here, right? Then when S1 and S0 are 1, 0, A2 from this set of inputs and B2 from this set of inputs will be activated. They will become the outputs, like so. And finally, for 1, 1. So this is how a dual 4 to 1 line multiplexer works. Problem 3. So we are required to construct a 16 to 1 line multiplexer with two 8 to 1 line multiplexers and one 2 to 1 line multiplexer. So we are required to construct a 16 to 1 line multiplexer using two 8 to 1 line multiplexers and one 2 to 1 line multiplexers. So we are also required to use block diagrams for the three multiplexers. So this will make our task easier. Instead of using logic circuits, we are just supposed to use block diagrams. So let's see how we can do this. First, we always start with whatever is given to us, right? So we are given in the question that we are supposed to use two 8 to 1 line multiplexers. So let's just draw these two 8 to 1 line multiplexers. 8 to 1 line multiplexer means it will have 8 distinct inputs, one output, and then 3 select lines, because 2 to the power 3 is 8. So 3 select lines for each of these multiplexers, 8 input lines, and one unique output line. This is directly from the question. Now, in the next step, see, we were supposed to design a 16 to 1 line multiplexer, which means we need 16 inputs. And you can see from these two multiplexers themselves that we already have the desired 16 inputs, 8 plus 8, right? So we have the necessary 16 inputs, and what we have left is these 6 selection lines. Okay, in the next step, let's see. Now, a 16 to 1 line multiplexer is supposed to have a total of 4 select lines, right? Because 2 to the power 4 is 16. So if we're going to design a 16 to 1 line multiplexer, it should have a total of 4 select lines. But we have 6 separate select lines. We need 4, we have 6. So we'll have to find a way to combine multiple select lines. And this is how we can do this, right? So what we have done is simply using taps, we have combined these three select lines S0, S1 and S2 and given them as distinct select lines for the two 8 to 1 multiplexers S0, S1, S2, and the same goes here. Alright, so now I've taken care of these three select lines. I'm only left with this one, and one will be taken care of because, as you can see, I still have a 1 2 to 1 line multiplexer to use, right? So I'll just put that multiplexer here. It's a 2 to 1 line multiplexer, which means it will have two inputs, one output, and a single select line. And now things are becoming clear, right? Because then this select line can be directly connected to this line. So first we can do is take these outputs of these multiplexers, make them the inputs of this multiplexer, take this select line which was previously unused, make it the select line from this multiplexer, and now your circuit is complete, right? We have 16 inputs, 8 plus 8. We have one output. We have 4 select lines like we were supposed to use, and we have also used two 8 to 1 line multiplexers and one 2 to 1 line multiplexer. And now the desired circuit is complete. Alright, that's it for this video. So just a quick recap. In this video, we discussed certain digital components. Specifically, we talked about decoders and encoders, multiplexers and demultiplexers, and finally, we took a look at some exercises where we were supposed to design circuits using smaller components of similar circuits.